Okay, so this work, this has been something that's evolving with some undergrads. We get good undergrads at Dartmouth. Morgan, who's our first MIT Dartmouth postdoc, and another graduate student. So what I want to do today, really I want to think about new ideas for dark matter detection. Is really describe electromagnetic gravitational bosonic wave mixing in curved spacetime. And of course, this should be of interest because curved spacetime is really neutron stars, white dwarfs, and black holes. So to do this, this is the 10-minute talk. And I want to just specialize to axions and axion-like particles today. So there are two key points I want to take away for this 10-minute talk. One, I want to show how gravity induces mixing in a model-independent way, regardless of whatever dark matter model that you have, okay? And the second point is that when you have this gravitational induced mixing, you can generate new oscillation probabilities that are reminiscent of the MSW effect for neutrinos, okay? Okay, so there are three pieces we need to go through in order to quickly review. I have make sure we do it in 10 minutes. I figure that this is largely familiar with everybody, so I can kind of give short shrift to everything. Okay, so dark matter density in black holes, gravitational wave effective theory, and basic axion mixing in Minkowski space. So dark matter spikes. So far as I know, the dark matter density spikes was first discussed by Gondolo and Silk. And this is plots from a more updated work. And essentially it's saying that, yes, there are density spikes, which everyone probably will say, duh, around black holes. But my major point here is just to say that it is something to consider curved spacetime and dark matter. So this, of course, just is more another plot from this paper. And yes, indeed, there is a spike nearby, and it's not, it's a really good thing to consider curved spacetime corrections when one thinks about dark matter evolution around compact objects. Okay, so moving on quickly. Gravitational wave effective theory. Now I know most of you probably know this. If you have a general gravitational wave and nonlinear wave, you can separate it from background curvature to some high frequency component. And so far as I know, I think Kip Thorne did this, but not really sure. Tried to follow it all the way back. And so just to let you know, L is the inhomogeneity scale background curvature. That's the thing that's most important to us. So I really want to look at L versus high frequency gravitational waves. And when you have a separation between the two, this allows you to define a gravitational wave. Okay. Okay, so with this, you can separate a metric from a background metric plus our metric perturbation, okay? And you can extend this idea also to other background fields. For example, this will be our axion and electromagnetic field, okay? The high frequency fields are the ones that are going to mix, okay? These are just dimensionless parameters, okay? And so you do this for all your quantities in your theory, your connection, your Riemann tensor, et cetera, and you have a lot of fun. Okay, third piece, keeping it moving. For axion photon mixing in Minkowski space, this is something that I think everyone knows about. Here, you simply have your photon polarizations that mix with your axion. The axion here is just A, it was phi before. So a lot of people have been thinking about this. I think the Rafel-Sadowski is like the main source, paper reference. There are Euler-Heisenberg effects, QED effects that one often considers. And the key thing is that the dimensionful parameters, like the mass term, are the things that set the oscillation length. Other dimensionful parameter, of course, is the axion photon coupling, which is that M, the dimension 5 operator. Okay, so what I just said, mass scales induce mixing. Mass terms, these mass scales set the oscillation length, just like we would expect. And so here they are. Isn't much to see here. And the key thing that I want to add is that when you consider curved spacetime, you have a new length scale, and it is like this MSW effect. So just to remind you what the MSW effect is, I'm with you. There is a new length scale as neutrinos propagate through matter. It's Fermi's constant. Okay, it's suppressed, but it's important. And it shows up also in the mixing. Okay, you can skip this. So what happens in curved spacetime? So you take your action, and we want to keep our Euler-Heisenberg corrections and our axion photon coupling just for comparison. And in this particular case, you have all your inhomogeneity scales. You want to make sure that your high frequency wavelength and all your inhomogeneity scales, we can still have those separations. Okay. And so for what I'm going to tell you, I kept everything to 1 over L to the 4th. And when I get there, when I get to local Minkowski space, I always covariantly average everything, the background quantities. Okay, so here's the gravitational equation of motion. And I write this down because I want you to see something. All the double derivatives are essentially Riemann tensors. Okay, and so they're the ones, so when you write down your mixing, you're going to get Minkowski plus curvature corrections. And if I went to a higher order in perturbation theory, there's going to be more and more and more. Okay. And this also is true for your axion and photon equations of motion. So what you get is in your local Minkowski space, after you've reduced down to your local Minkowski space, something that looks like your axion photon mixing. But there are things that are now special, or at least I hope they're special. These are the covariant average quantities. And of course, I didn't mention this, but I want to tell you that the reason why you're going to local Minkowski space is because you need a co-moving frame in order to calculate the mixing. Okay, so the key thing that the first takeaway that I want you to take away from this is that in the limit that the axion photon coupling is to 0, you still have mixing. There's this mixing that's generated by energy momentum interactions. And they are notated by the purple arrows. Okay, and it's, well, I call this universal, but we can come up with a better name. So we have essentially what we've had before. We have our lambda tilde is our axion photon coupling. These are our energy momentum corrections from the interactions from the energy momentum tensor. So we have our Hamiltonian. We can diagonalize it. And so you get all these wonderful probabilities, okay? And each one of these probabilities you get, again, because you've gone to local Minkowski space, the takeaway thing for a 10-minute talk, Minkowski plus curvature correction, because we set this up in a local Minkowski space, okay? So more probabilities. I did not think I have time for this. I probably don't. But for those of you who are interested, I can show you plots of how these energy momentum corrections compare with the axion photon coupling for this particular model. Anyway, concluding thoughts. Curved spacetime adds a new length scale. This is analogous to the MSW effect, okay? And the interactions from the energy momentum tensor that pop up in your mixing equation are model independent. And thank you for listening.
Thank you.
Can I say one more thing?
Sure.
If this is the frozen north, I think we're getting 8 inches of snow in New Hampshire tomorrow. So anyway.
All right. Questions to Devin? Yes, Jesse.
So in terms of the compact objects you're talking about, these are objects that do or do not carry electromagnetic charge.
The dark matter?
You said this is in the presence of a compact object. And that compact object has curvature. Does it have electromagnetic charge?
Well, I only did this for Kerr, but it could.
So you did this for Kerr?
I just did it for Kerr. I mean, certainly you can. I mean, that would be really fun to add some charge to your black hole.
So, so normally, as you said, we usually get mixing in the presence of a background magnetic field for usual axion-photon mixing.
That's right.
So, I missed the formula that showed the axion-photon mixing in this geometry. What's the thing that plays the role of the effective magnetic field?
The effective magnetic field.
Or is there something that plays the role of the effective
That's
magnetic
right.
field?
It was a little bit excluded. Well, I didn't make it very clear. It's in there. It's like the what I wanted to do is show mixing, but yes, I assumed that there was some electromagnetic field surrounding the compact object, whatever it is.
Sorry, and that's your V prime term?
That could be, yes. So that would be my B bar term.
Right, thanks.
So yes, it's in there. It's, I don't know if you all remember the old commercials about tomato sauce. It's in there, okay. Okay, I'm dating myself.
More questions to Devin? All right, let's thank him again.